Hello all, welcome back to my YouTube channel all about VLSI. Hope you're all doing good. I hope my screen is visible and my voice is audible, right? So let us start today's session. So before starting today's session, please make sure that you have subscribed to our channel all about VLSI, right? Yeah. So today's topic is we will discuss about half wave and full wave rectifiers. So today's topic is half wave rectifier. We will start with the discussion of half wave rectifiers, and in next session we will discuss with full wave rectifiers. Okay. Yeah. So basically, this half wave and full wave rectifiers are the applications of diodes. Okay. So half wave rectifiers and full wave rectifiers are applications of this PN junction diode. Okay. So what is meant by half wave rectifier? Let us see now. A half-wave rectifier is a circuit that converts alternating current AC current into pulsating DC current. Okay, so it converts the AC current into a pulsating DC current by allowing only one half cycle of the AC signal. Okay, so it will allow only one half of the AC cycle of the AC signal to pass through and blocking the other half cycle. It is typically uses a single diode to achieve this function. So basically, it will look like this. So this is a AC signal. So the input of this circuit, this is a half wave rectifier circuit. Actually, we'll discuss about the circuit. So first we will discuss about the behavior of this particular circuit. Okay. So this is half wave rectifier circuit. Half wave rectifier circuit HRC. Okay. So for this half wave rectifier circuit, this is our input. This is our input AC signal. Input AC signal. And this is our output pulsating DC signal. Output pulsating DC. Okay, it is pulsating DC. Pulsating DC signal. So in the input, if you observe, it is a sine wave. Okay, this is a positive half. Okay, and this is a negative. Okay, this is high and this is low. Okay, this is positive peak and this is negative peak. And at the output, if you observe, we will get only the positive side. Okay, only the positive side. The positive side, negative side will be discarded. Only the positive side will be given. So this is the functionality of a half wave rectifier. So this is a functionality of a half wave rectifier. Only the positive signals are given and the negative side are discarded. Okay, now so let us see how it is this particular circuit is behaving. So we have given a diode. Okay, so this diode is forward biased. This diode biased. Okay, so here what happens if the voltage is high, then this diode conducts. This diode conducts. Okay, since the voltage is high and it is forward biased, so for the positive voltage, the diode conducts and the current will flow, or the current will flow through this diode. So at the output, if you can see, there will be voltage across this resistance RL. So that's why we are getting a positive voltage here. And when the input voltage is negative, for this negative voltage, the diode will be in reverse bias condition. Okay, for this negative voltage, the diode will be in reverse bias condition. For the positive voltage, for the positive input voltage, the diode is in forward bias, and for the negative voltage, the diode is in reverse bias condition. So when the diode is reverse bias condition, we have already seen that if the diode is in reverse bias condition, no current will flow through this diode. It will act as an open circuit. So for the negative voltage, the diode will work as an open circuit. Okay, open switch. So no current will flow through the diode. So if there is no current flowing through the diode, then the resistance through this resistance, external resistance or load resistance, you can say RL is a load resistance, there is no current flowing through this load resistance. Since the diode is open, or it is acting like an open switch, so if there is no current flowing through this load resistance RL, then there will be no voltage drop. Across this resistance. There will be no voltage drop across this resistance. So that's why here for the negative input voltage, the output is equal to 0. Since the diode is working as a reverse bias for the negative input voltage. Okay, now so this is how the diode is working as a half wave rectifier. For the input positive voltage, the diode will work as a forward bias condition. The diode will be in forward bias and it will conduct the positive voltage, and for the negative voltage, the diode will be in reverse bias and there will be no voltage drop across the external resistance. So this is how the diode is used as a half wave rectifier. Okay, so basically a half wave rectifier converts alternating current into pulsating direct current. Okay, this is a half wave rectifier functionality. Now, so the theory here it is written what we have discussed previously. So during the positive half cycle of the AC input, the diode is forward biased and it conducts and allowing the current to flow through the load resistor. During the negative half cycle, the diode is in reverse biased and does not conduct, blocking the current flow and resulting no output voltage across the load. That we have already discussed here in this slide. Okay, so this is about half wave rectifier, how the diode is acting as a half wave rectifier. And the output here is a pulsating DC. The output here it is a pulsating DC signal that has same frequency as the AC input. Here if you observe, the input frequency is equal to output frequency. There is no change in the frequency. This is also very important point. Input frequency of half wave rectifier is equal to output frequency. Here there is no change in the frequency at all. Okay, there is no change in the frequency. Input frequency is equal to output frequency. So the output is a pulsating DC. The signal only consists of a positive and with same frequency as the input, but here the signal only consists of positive half cycles. We have already seen this. The output signal only consists of positive half cycles. Negative half cycles are removed. Only the positive half cycles are present in the output. Okay, yeah. So that is about half wave. Now, what is the output voltage? DC output voltage. The average DC output voltage for a half wave rectifier can be calculated as VDC is equal to V peak by pi. So this is a formula for calculating the average output voltage. VDC is equal to V peak divided by pi, where V peak is the peak voltage. V peak is the peak voltage. Okay, what is this peak voltage? For example, this is our output, right? This is the output we are getting from a half wave rectifier. This is the output we are getting from a half wave rectifier. So the peak voltage is the highest voltage of this particular signal. Okay, so this is the peak voltage, Vp. Okay, divided by pi, we get the output DC voltage or average voltage. So this is how we are going to find out the DC output voltage. And coming to the efficiency of half wave rectifier, the efficiency of half wave rectifier is only 40.6%, which is quite low because it is only utilizes half of the input signal. Here if you observe the input signal, only the positive edges are being used. Only the positive edges are being used and negative edges are being trimmed off. So that's why the efficiency is very low. That is, it is equal to 40.6%. Okay. That is, the diode is working only for the positive half cycles. The diode is off for other negative half cycles. So that's why the efficiency is very low. That is, it is equal to 40.6%. So this is the efficiency of the half wave rectifier. And wait a minute. Yeah. Now let us see the effect of barrier potential on the half wave rectifier. So let us see this diagram again. We have a ground and a voltage source minus plus and a diode which is present here and load voltage RL, okay, which is grounded. And this is our input signal. This is our input signal, right? Now here, let's say this is V peak voltage of input voltage. So Vp in peak voltage of input, peak input voltage also you can say, peak input voltage. Now in the previous case, when we were discussing about the half wave rectification process, we haven't considered any barrier potential or anything. Okay, since just we have considered the diode to be an ideal diode and we have done the process of rectification. Now in this second case, in this second scenario, what we are going to consider is, we are going to consider barrier potential. We are going to consider a potential called as barrier potential. We are going to consider a barrier potential. What is barrier potential? Everything we have discussed in our previous session. So if you haven't watched that, please go back and rewatch those sessions if you are not sure about what is meant by barrier potential. Okay, so we have discussed about what is meant by barrier potential. So it will be around 0.7 for our silicon made diodes. Okay, so now we will consider the case of the diode is consisting of barrier potential of 0.7 volts. Now, so if this is the input that is given to the diode, so what is the output? So in the previous case, our peak voltage was same as the input voltage. Our output voltage, the peak voltage, was same as the input peak voltage. That is, Vp out was equal to Vp in. Since the diode, we considered it as an ideal model, so the output peak voltage was same as the input peak voltage. But here we are considering the barrier potential, so the output peak voltage, now it will be equal to output peak voltage, now it will be equal to input peak voltage minus 0.7. Okay, there will be a reduction in the 0.7 volts in the output peak voltage. That's it, simple. So in the previous case, we have what we have seen, there is no change in the peak voltage. The input peak voltage is equal to output peak voltage in the case of ideal diode. But when we consider the barrier potential also, barrier potential of the diode, then the output peak voltage will be equal to input peak voltage minus 0.7 volts. That's it. So there will be small reduction in this amplitude of the voltage. So if this is the waveform, what we were getting, let's say if it is 2 volts, what we were getting, then at the output, let's say this is our input, then at the output we will get around some 1.3. So there will be some reduction in the amplitude of the output if we consider the barrier potential of the diode. So it will be equal to 1.7 volts. Okay, that is the effect of barrier potential on the output peak voltage. Now, peak inverse voltage. What is this peak inverse voltage? So peak inverse voltage, also known as peak reverse voltage, PRV. So peak inverse voltage is also known as peak reverse voltage, is a maximum reverse voltage a diode can withstand. So it is a maximum reverse voltage a diode can withstand without breaking down. So how much maximum reverse voltage a diode can withstand without breaking down is called as peak inverse voltage, that we have already seen, right? So in the reverse bias condition, the diode will not at all conduct. So if we go on increasing the reverse bias voltage, if we go on increasing the reverse bias voltage, the diode will stay up to some potential, right? Which we have discussed. Okay, so the maximum voltage the diode can withstand, which is called as peak inverse voltage. So in other words, it is a maximum negative voltage that can be applied across a diode in the reverse bias mode without causing a permanent damage. So what happens if the reverse voltage has increased beyond a certain point? Then a huge amount of current will flow through the diode. Reverse current will flow through the diode, that we have already seen with the VI characteristics of the reverse bias diode, right? So from that we can observe that if the reverse voltage has increased beyond a certain point, then the reverse current will, a huge amount of reverse current will flow through the diode that causes the damage to the diode. So the peak inverse voltage is the maximum amount of voltage so that the diode is not damaged without causing the permanent damage to the diode. That high voltage, that maximum voltage is known as peak inverse voltage. So from the graph, if you observe, this point is called as, in the negative point, if you observe, this point is called as peak inverse voltage minus Vp. Okay, this is known as peak inverse voltage. Peak inverse voltage. So this point is known as peak inverse voltage. So it is known as peak inverse voltage is given by PIV, which is equal to Vp input. Vp input. So that is about the half wave rectifier and peak inverse voltage. How to calculate the peak inverse voltage we have seen, and how to what is the effect of barrier potential on the half wave rectifier output, that also we have discussed in our session. Yeah. So that's all for this session. So if you have any doubts or queries, you can ping me in the chat, or else we can end the session. Okay. So in this session, we have completed with the introduction and explanation of half wave rectifier with the peak inverse voltage and effect of barrier potential on the output of half wave rectifier. Yeah, one more thing, application. Yeah, applications of half wave rectifiers are commonly used in low power applications where simplicity and low cost are most important than efficiency. So in the cases where we do not want any efficiency, we don't care about efficiency, we want only a less power to be consumed. In those cases, we are going to use this half wave rectifiers. Example, small battery charges and simple DC power supplies, we are going to use this half wave rectifiers. Okay. Yeah. So that's all for this session. Thank you.